As processing demands escalate, single monolithic silicon chips are hitting the reticle limit, the maximum physical size a fabrication tool can reliably print. To bypass this physical constraint, manufacturers are disaggregating large chips into smaller, distinct modules. Printing smaller dies directly increases the number of usable chips per wafer, optimizing the overall manufacturing yield. But dividing a processor introduces a severe engineering consequence. Signals that once traveled across highly efficient microscopic on-die metal layers must now exit the silicon and cross the package substrate to reach the next chiplet. Historically, moving data off-die meant relying on standard interconnects like PCIe or Ethernet. Those protocols are engineered to drive signals across long distances over printed circuit boards. Driving data across a motherboard requires complex analog circuitry. That complexity imposes a massive communication overhead, typically costing between 5 and 10 picojoules of energy for every single bit of data transferred. The analog complexity of these legacy links also creates a secondary penalty. Exiting a low-power idle state takes several microseconds, forcing the circuits to stay powered on even when data isn't actively moving, just to avoid the wake-up delay. This data table details the specifications of the Universal Chiplet Interconnect Express, or UCIe, advanced package standard. It drops base power to 0.25 picojoules per bit and scales bandwidth density into terabytes per millimeter. To make a chiplet-based system economically and thermally viable, engineers had to physically reverse engineer the interconnect to close this power gap, allowing a partition system to function exactly like monolithic silicon. To understand how those efficiency metrics are achieved, we have to examine the physical edge of a single chiplet, known as the shoreline. In standard 2D packaging, the distance between the connection points, the bump pitch, ranges from 100 to 130 micrometers. Advanced 2.5D packaging techniques, like silicon interposers or embedded bridges, compress that bump pitch down to a range of 25 to 55 micrometers. This comparative map illustrates the geometry of bandwidth density. Shrinking bump pitch linearly increases connection points, inversely as the square of the distance. This upgrades a 16-lane data module to a 64-lane module without taking up additional shoreline. Multiplying the raw number of physical wires translates directly into massive aerial bandwidth, allowing terabytes of data to move per second across a tiny physical footprint. The alternative to building denser physical connections is trying to push more data over fewer wires by scaling up the analog frequency to 100 GHz or higher. Pushing extreme frequencies over copper requires aggressive voltage. It generates excessive heat, creating a power ceiling that makes high-density chiplets impossible to cool. By utilizing the tight geometry of microbumps, hardware architects can instead deploy wider data paths running at slower digital frequencies, completely avoiding the power tax of extreme analog scaling. A standard interconnect traversing a motherboard often needs to push signals across 100 millimeters or more of copper trace. At those lengths, a printed circuit board is a hostile electrical environment, highly susceptible to insertion loss and crosstalk interference from neighboring components. However, inside an advanced package, the physical distance between two separate chiplets shrinks down to a microscopic gap of less than 2 millimeters. This block diagram compares the physical layers of a long-distance external link and a microscopic UCIe advanced package link. Both initially outline components for transmitters, receivers, clock recovery, and RX termination. RX termination absorbs signal reflections on long channels, drawing continuous high power. But because a 2 mm advanced package channel is isolated and stable, this entire logic block is completely removed from the UCIe design. This hardware reduction allows the package to utilize simple, unterminated circuits that operate much closer to standard digital logic, drastically cutting base power consumption. This eye diagram plots signal voltage over time on an unterminated link. The wide open center proves that even without termination circuits, signal integrity remains excellent at speeds of 32 gigatransfers per second. Stripping away that complex analog compensation, a subtraction made possible entirely by the physics of the ultra-short channel, drives the base power metric down towards 0.25 picojoules per bit. That physical simplification also solves the secondary problem of legacy I/O, the microsecond wake-up delay. External links rely on a derived clock system. The transmitter sends a raw, complex data stream, and the receiver has to mathematically extract and reconstruct the timing clock from that messy signal. When exiting an idle state, the receiver's clock recovery circuits need several microseconds to lock onto the signal and stabilize before a single bit of actual data can be processed. The UCIe advanced specification solves this by utilizing a forwarded clock. With identical physical trace lengths, a dedicated clock line runs exactly parallel to the data lines, allowing the receiver to completely bypass the heavy computation of clock recovery. Without waiting for recovery circuits to lock, a UCIe link can wake from an idle state and stabilize in less than 1 nanosecond. That sub-nanosecond reaction time permits extreme dynamic power gating. The physical link can be instructed to power down and instantly wake back up on a nearly cycle-by-cycle basis, depending on exact processing demands. This graph plots bandwidth utilization against power consumption. While external I/O suffers from a high, flat plateau of idle power drain, the UCIe interconnect produces a perfectly linear slope starting near zero. If a computing task requires exactly 10% of the interconnect's peak bandwidth, the system physically consumes exactly 10% of its maximum power. Replacing derived clocks with forwarded ones aligns the energy profile of the interconnect with the actual data load. Power consumption now scales directly with bandwidth, removing the constant passive drain found in legacy clocking architectures. The microscopic gap between two partition chiplets dictated the engineering of the entire UCIe standard. The tight geometry of microbumps allows for an immense number of parallel wires, resulting in wider data paths that operate at highly efficient digital frequencies. The physically short distance of those paths guarantees pristine signal integrity, eliminating the need for heavy analog RX termination and complex clock recovery circuits. The result is a standard that delivers terabytes of bandwidth per millimeter, achieves sub-nanosecond wake latencies, and drops base power to 0.25 picojoules per bit. By utilizing the specific physics of advanced packaging, hardware architects have engineered an interconnect that strips away the analog overhead of legacy I/O. A disaggregated multi-chip system can now behave, electrically and logically, exactly like a single monolithic die, allowing hardware architects to seamlessly scale compute density far beyond the rigid physical constraints of the reticle limit.